Hi, I'm Mark Seager, Intel Fellow and CTO for the HPC ecosystem, and I'll be talking about Coral and Intel's Scalable System Framework. It's our path to Exascale. What we've noticed in the last couple of years is that traditional HPC is expanding beyond the traditional physical modeling techniques based on partial differential equations to also including big data. These big data sources are the simulations themselves and the quantification of uncertainty activity, where you're trying to get error bars and understand where the sources of errors are in your simulation. But also experiments. DOE has a large set of experiments producing petabytes of data per year, and also streaming data that is coming from satellites and internet sources and so forth. The other thing that we're seeing is that there's a new access methodology that's coming about through an HPC in the cloud access methodology, which is for both public and private cloud infrastructures. This would, coupled with the challenges of Exascale, require a different approach to solving these problems, and it involves innovation across multiple vectors. Of course, our traditional area of innovation is in the processor performance, coupled with our partnership with memory vendors to produce next generation memory technologies. And then there's a new area we're innovating in called Interconnects, and this is where the OmniPath technology comes in. And of course, to get to Exascale, you have to focus on power efficiency and reliability and resiliency because of the large number of processors and scale of the system and applications that are required to solve those problems. But we want to do that within the framework of a standard programming model for parallelism that preserves the investment of application programmers and ISVs within the HPC community. So all of this then requires a tight integration, and that tight integration is done across our product line, processors, interconnect, new storage, and future memory devices, and also our Intel Parallel Studio co-development tools, and our Intel Enterprise Edition for Lustre software, and also a new software technology we're calling Performance Peak. The Intel fabrics are optimized for HPC. They're based off of our TrueScale technology line that was acquired a couple of years ago from QLogix, and is being integrated into the processor package in the KNL timeframe for the Theta system and other systems that the DOE and other sites have purchased in the late 2015 timeframe. And what it allows us to do is to reduce the amount of power required for a given bandwidth, or increasing the bandwidth by a factor of 4 and keeping the power the same. That and tightly coupling it with the processor allows us to reduce the latency, and it also allows us to vastly increase the messaging rates of these interconnects. And the first generation of this Intel Fabric product called OmniPath 1 will be available by the end of this year. This co-design process happens as a tight coupling between the hardware, which I've described already, and the software design, and that's why we're very excited about our partnership with Argonne and DOE, because they bring the applications, and it's all about the science and mission deliverables that these systems produce, and that is the reason we build these things. And so a tight coupling with the applications, the middleware, and the OS, and a co-design with the hardware, compute, storage, I/O, interconnect is how we're approaching this problem. As I mentioned, it's based on 4 components, and we're very cognizant of the fact that we're going after supercomputing and exascale, but at the same time we also have to scale down to much smaller clusters to make it cost effective and catch that volume segment as well. And we want to be able to go from desktop basically to exascale with a single framework. We want to also cover 2 spans of the compute continuum today into one framework, compute and data-centric computing. So this is, very little storage, a lot less interconnect bandwidth, a lot less I/O bandwidth. Here, it's the exact opposite. You want lots and lots of storage. You're willing to give up some of that compute, and as long as there's a very fast interconnect to move the data around with. And again, keep that based on standards for the programmability and portability of applications. One of the other thing that we want to be able to do here is not only have this framework that spans this wide range of sizes of system, but also the workload that runs on them. We also want to be able to have this framework span multiple generations of platforms so that you have portability across different platforms within a framework generation, but also have portability in time of these applications across multiple generations. So we have two approaches, two basic approaches here. One is the traditional Beowulf COTS Linux cluster approach, where it's commodity off the shelf components put together in standard racks with air cooling in basically a fat tree interconnect where we define scalable units, and at the top of each rack in that scalable unit are top of rack switches that are the first stage of the interconnect, and then the second stage of the interconnect is a heavy duty spine switch that allows you to hook multiple scalable units together. In the KNL time frame, in 2016, we have a half a petaflop single scalable unit, and strapping 18 of those together with 3 spine switches with OmniPath 1, you can actually get to 10 petaflops very cost effectively. But if you want to go to hundreds of petaflops, then you need a more dense design, water cooling in the KNH generation, and also more on-package memory. And then a new memory technology that brings the file system very much closer to the processor itself. And this is a gradual evolution that we're seeing that we think will allow us to span the space from COTS Linux clusters all the way to Exascale systems. In terms of thinking about the future and where we go from here, we are focusing on multi-core in our Xeon line and many-core in our Xeon Phi line, but in the future we're really power limited, and we want to be able to have more flexibility in the type of applications that these processors run. So we're thinking about mixing the types of cores that are available. We're also thinking about integrating FPGA technology and accelerator technology onto the processor die for 2 reasons. One, to offer our OEM partners the ability to differentiate, and also offer the ability to, for specific verticals, offer way more price performance and performance per watt type characteristics. And with that, I will talk about the new storage paradigm. Basically, at every level of the storage paradigm, we're trying to change the model to bring more bandwidth to the processor by moving local memory into in-package memory. We're also trying to bring non-volatile storage that typically is either SSDs on the system or a parallel file system directly onto the node with the processor, and also increase the capability of burst buffer technologies, and then have parallel file systems down here based on 3D NAND flash. If we're able to accomplish all 3 of these goals, basically we'll be able to eliminate mechanical devices in the memory hierarchy or the storage hierarchy here, and provide an order of magnitude or more performance boost at every level while reducing latency. One example of this for the Aurora system is our function shipping mechanism that allows applications to take advantage of locally connected SSDs on the system through an I/O forwarding mechanism that allows us to have a global burst buffer capability on the system itself, or the user can point it at the Lustre parallel file system, which is disks connected on a SAN, a traditional parallel file system, and it's fairly transparent to the application. You either mount this file system or you mount the Lustre parallel file system, and the same I/O operations apply. We'll also have a burst buffer manager software that migrates data off of the burst buffer according to the policies of either the computer center or the application itself, which allows a migration of data in sort of a 10-to-1 ratio. 10 times you write it here, and then you write out the very important results out to the parallel file systems. And then on restart, you would backfill the application data in. And again, the same programming model that's available today for KNC and will be available for KNL and the next generation, as well as the Xeon line, will be available on future generations of this architecture going through the Exascale era. And so it's a single, broadly configurable framework to meet both the requirements from a hardware perspective, but a software perspective over multiple generations of systems. And with that, I'll close and say thank you for attending.